Continue with example 2 in lesson 3-5. Understand how a multiple zero can affect a graph. How does a multiple zero affect a graph of a polynomial function? The multiplicity of a zero of a polynomial function is the number of times its related factor appears in the factor form of the polynomial. Notice the behavior of each graph as it approaches the x-axis. What can you conclude about the multiplicity of a zero and its effect on the graph of the function? So if you look at all these examples below, let's look at the multiplicity of a zero. In this graph, we have two zeros, right? So there are going to be two zeros, two real zeros. The graph looks like a polynomial function with degree equal to the multiplicity of the zero, which is going to be squared. Let's look at this part. Well, there are two zeros here too, but the end behaviors are different. So if we have the end behaviors going to the opposite ways, we know they're odd degree polynomial, right? From lesson 1. This is what we first learned, right? And so we know there are going to be three zeros, three real roots, but this may be a duplicate. So when your graph touches your x-axis and then goes up again, so like in this case, you have a positive interval and then it's still positive, but there's a zero, right? There's a turning point. But this is when you have a zero both times. So you have two zeros, two turning points, and then it just goes up again. It's like, oh, it's a turning point. Oh, but then it's a turning point again. And so it's supposed to turn, it's a zero that turns positive to zero, positive to negative, but then it's another zero, so it turns negative to positive. I don't know if that makes sense. But sometimes you have two zeros that are the same. So, but still, there are three actual zeros if we separate the duplicates. This one is a cube and another factor, so this is a quadratic. We know that by the end behavior that it is going to be even degree function. We have only two zeros, but we have several turning points, right? We have a turning point here, possible turning point here, right? So the graph decreases and then increases, kind of decrease, but like increases again. So we know that this is going to be duplicate because it increased and then increased again. So there must be duplicates here that changed your direction of your graph. So you can tell that, oh, this is not just a quadratic function where you have a curve, just one curve like that, but there are several curves. All right, let's look at this one. You have two zeros, two real roots, but it's an odd degree function. Looking at the end behavior, we know that it's odd degree, so it's going to have two turning points. Starting here, increases and then turning point, decreases, turning point, increases. But so if we have a normal one that crosses the x-axis separately, we should have three different zeros. But then this interval is positive and this interval is also positive, right? And this is the only one that's negative. So here that means the graph touches the zero and that's also a turning point, and then it goes back up again. So that's a duplicate. Yeah, so a lot of times if you look at the graph, you can explain the polynomials by describing the end behaviors, the zeros of the function, and here multiplicity of a zero. So how many zeros we have would tell us how many factors we would expect to have. right? So because we have the factor theorem, the zero factor theorem, right? We know that the factors are related to 0. If one factor is equal to 0, you have to have a 0 of that function because anything multiplied by 0 is 0. So they're very closely related. So when the multiplicity of 0 is odd, the function crosses the x-axis. But when the multiplicity of a 0 is even, just like all these examples, the graph has a turning point at the x-axis. All right, so looking at these examples, let's practice if you can describe the behavior of the graph of the function at each of its zeros. So pause the video, see if you can describe it by yourself. Come back when you're ready to discuss. Okay, are you ready? Let's look at 2a. We have a function that has 1, 2, 3, 4, 5, 6 factors. But this factor x minus 1 is a duplicate with a fourth power, right? So then it'll appear like we have 3 zeros, 3 real roots. So looking at the multiplicity of 0, the multiplicity of a 0 for this function is odd. So we know the function crosses the x-axis at x equals 0 and -4 and +1, right? So when do we have a turning point? Well, we have to figure that out. We have to see where the interval is positive or negative. So we know that there are 3 types of zeros: 0, -4, +1. And so we have the intervals from -infinity to -4, right? Wait, that should be a parentheses. And then -4 to 0, 0 to 1, and 1 to +infinity. So we have to check these intervals. Anything less than -4 would give us the whether it's positive or negative on that side. So plug in -4 here, that's 0. Plug in something that's less than -4, so maybe -5. So that's a -5. And then -5 plus 4, negative. -5 minus 4 is going to be negative, but it's multiplied 4 times. So negative, 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 negative. So it's a positive. Positive times negative is a positive. So this is going to be positive, okay? -infinity to -4, that's going to be positive. And then -4 to 0. So check. This is, so see if -1, let's say -1. That's -1 and that's positive. And then that's 0. Wait, no, that's negative. So negative, 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 negative. And so it's going to be positive times negative. So this is going to be negative. And then this one, 0.5. So that's positive. And then that's positive. And then that's still negative. But negative times negative times negative times negative is going to be positive. So this is going to be positive. And then 2. Pick a 2. That's greater than 1, right? That's positive, and then that's positive. So it's going to be positive. So here we know that from -infinity to -4, it is positive. And then from -4 to 0, it's negative. And then from 0 to 1, it's positive. And then 1 to infinity is positive. So you can't just draw your graph like this because they're both positive. We know there's a 0 at 1. So you have to touch the x-axis at 0, at 1. So we have an odd degree function that has an end behavior, both looking upward as x approaches negative and positive infinity. But we have this duplicate, this 0, that has a turning point at 0 equals 1, right? So how can we describe that? We need to be able to describe it in words. So we can say that the graph, it's not hard. You can just say that the graph crosses the x-axis at the zeros -4 and 0. And what about 1? 1 is a special one that has a turning point at the 0, right? So, and has a turning point at the 0, 1. Okay, so that would be part A. So this is a process for you to figure out the zeros, the multiplicity of zeros and where the turning point would lie. You have to check their intervals. Okay, so in the same way, part B will have a graph that crosses the x-axis at the 0, 1 and has a turning point at the 0, -2. Okay, so yeah, it's not too hard, but just notice that we have a turning point. We have a case where we have a turning point at 0, and that happens. So in order to check that, you just have to check the intervals and see whether they're positive or negative. Okay, if you have any more questions, please ask me in class. But let's move on to example 3. Find real and complex roots, complex zeros. What are the real and complex zeros of the polynomial function shown in the graph? Let's look at this graph. We have an odd degree function here, right? We have the end behaviors that are opposite direction. So we know it's an odd degree function. How do we know if it's a 3rd degree, a 5th degree, a 7th degree, or yeah? We know it's not linear because they're curved, but we know it needs to be at least 3rd degree because we have 2 turning points, right? And then we just have 1 real 0. But we see that there are 2 turning points. So this is a quadratic if we just have 1 turning point, but we have 1 more. Yeah, so step 1, you can use the graph to determine one of the zeros of the polynomial, which is 2, right? The function crosses the x-axis at x equals 2. And so how do we confirm that 2 is a 0? The function, by using our function here, f of 2 should equal to 0. So you can plug it in here, 2 cubed plus 2 squared minus 3 times 2 minus 6, and it should be 0. If not, this is not exactly 0. So 2 is one of the roots. By the factor theorem, we know that one of the factors would be, if x is equal to 2, we know that one of the factors should be x minus 2, right? So yeah, x minus 2 is one of the factors. So what do we do after that? We've learned division, right? So we're going to factor this factor out from our original polynomial to see other factors and see if we can factor that. Okay, so first, we're going to divide after that. So first figure out the 0 from the graph, and then use synthetic division. You can use 2 and the coefficients, right? 1, 1, -3, -6. Put down the first leading coefficient, and then you multiply 2 times 1, 2. Add them, multiply, add them, multiply, and you get a 0. Nice little 0, no remainder. So then it's a nice little factor with x squared plus 3x plus 3. So if you factor this out, it's kind of hard to factor a big polynomial, right? But by looking at the 0, you can figure out one factor, and then you can divide by using synthetic division, and then after that, you can use quadratic formula to find the remaining zeros for this formula. Remember, when you have a quadratic function, you can determine a, b, and c for your with your coefficients, and then you can use quadratic formula to figure out the non-zero roots. So the zeros are, there are many zeros, but by graph, we can just see the real 0, which is 2, and then there are imaginary roots, and we can figure it out using division and quadratic formula. Yeah, so these are the steps to find all the zeros possible from a polynomial. So 2 is the real root, and then -3/2 plus or minus √3/2i would be the other two roots. Let's look at try number 3. What are all the real and complex zeros of the polynomial function showed in the graph? So look at parts A and B. You have the graphs and the equations given. So using these information, see if you can find all the real and complex zeros. Pause the video, come back when you're ready for answers. Okay, are you ready? Yeah, so the first step, determine the real root. It appears that we have 3 as a 0, right? So you can check if 3 is really the real root by plugging in 3 for your function and see if it equals 0. It will, but just double check, right? It is equal to 0. So 3 is our 0. And then so that's step 1. And then step 2, you're going to use synthetic division. We know that there is a factor of x minus 3, right? So divide your factor. So this, using synthetic division, we're going to divide your polynomial. So 3 divided by 2 and -a, and then just make sure that your terms are not missing any terms in between the powers. Okay, and then you put down the 2, multiply 3 times 2 and add them, -2, multiply, add, multiply, add, and a nice little 0 as a remainder. Okay, good. So if we factor it out, if we divide it, we know that this function is equal to x minus 3 times 2x squared minus 2x plus 3. Okay, and the third step, you're going to use the quadratic formula. -b, your a is equal to 2, and b is equal to -2, and c is equal to 3. So -b plus or minus 4b squared root b squared minus 4ac over 2a. And so using this formula, you can plug in your a, b, and c's. -b, so 2 plus or minus -2 squared minus 4ac over 2a. And you simplify, you should be able to get 1 plus or minus I root 5 all over 2. Okay, so last step, just write your solutions. The real and complex zeros of the polynomial function for part A is x equals 3 and x equals 1 plus or minus I root 5 over 2. That's your final answer for A. And using the same steps for part B, you should be able to get 2 real roots. So x is negative 2 and 2. And if you factor this out and use division, you will be able to get I, positive I, and negative I for this one. All right. So that was example 3, finding real and complex zeros. We'll continue with the next example in the next video.